various transitions require different wavelengths. So at a particular wavelength, a molecule may absorb some light, but if you use a different wavelength, then the absorbance could increase or decrease depending on the particular transition that is taking place because of the relationship between the energy of the radiation and the energy of transition within the molecule. So the proportionality is dependent on the wavelength, or the absorptivity is dependent on the wavelength of the molecule, the wavelength of the light and the molecule in question. So when a monochromatic radiation is passed through a solution, the decrease in intensity of radiation depends on molar absorptivity, which we have just listed earlier, and the concentration. So by relating those two, then we are able to determine the concentration. This is a graphical representation of what is actually happening. That if you had several concentrations of the same solution and you measure the absorbance after doubling the concentration, then you find that the transmission, the amount of light transmitted through the samples decreases by a half for every doubling of the concentration of solution. So in other words, we are saying that the absorbance increases exponentially, or transmittance decreases exponentially as the concentration of the sample increases. So that is the equation representing that. There is a bit of mathematics there that we will not go into, that will eventually coalesce into Beer-Labert's equation. So this you can check up for your own interest. Okay, so eventually we are saying that absorbance is dependent on concentration if the path length is constant. Okay, this E is the absorptivity, or the ability of the molecule to absorb, and it is the proportionality constant. Similarly, transmittance also decreases exponentially as the cell length or the path length increases. So if we were to use the same concentration of the sample, but then vary the width of the cell, immediately we double the path length, or we double the size of the cell, then transmittance also decreases by half. So similarly, that equation relates the transmittance or absorbance to the path length, or the path the light passes through the solution. So when combined, then we get absorbance is a function of concentration and path length and the molecule of interest. So this equation is for absorbance. We get for every absorbance, it will be determined by the molar absorptivity, the concentration, and the path length. Some of those entities have their units, but absorbance has no units. So the units of concentration and path length will be cancelled by the units of molar of the absorptivity. In particular, when we are applying this law, we generally do not use molar absorptivity, we tend to use what is known as specific absorptivity. And this is the absorptivity of the substance when the concentration and path length are stated. For example, we commonly use what is known as A1%, 1 centimeter, which is the absorptivity of a 1% solution in a 1 centimeter path length. So this specific absorptivity can be used in place of molar absorptivity. So in that way, we are able to directly relate the mass of a substance to the absorbance rather than going through the molar conversions. However, under certain conditions, the Beer-Lambert's law does not directly or proportionately relate to concentration, and we'll list a number of those conditions that may prevent the quantitative application of UV visible spectroscopy. So if there is no direct proportionality, then the law breaks down and cannot be used to determine the concentration. These conditions include, or the necessary conditions for the application of Beer-Lambert's law include that the absorbing molecules must act independently of each other. So that means that the ability of a molecule to absorb is not affected by the state of the neighboring molecule. Okay, so when the molecules are acting independent of each other, then the law is able to hold within that particular condition. Another condition that is necessary is that the medium must be homogeneous. So if we are saying that you are testing using UV visible spectroscopy, the solution must be uniform. So you expect that if you take a sample within that path length or within that path of the light, then you are likely to get the same quantities of the absorbing molecule. That is that the medium must not scatter the radiation. So that means that the solution should not have particles. And this is achieved by proper filtration of the solution. In addition, the incident radiation must consist of parallel rays. So this is important because we have said that the intensity of absorption depends on the path traversed by a ray of radiation. So if they are not parallel, that means some of the part of the rays will cover a shorter distance while others cover a longer distance, and that will affect our measurements. Fifth, the incident radiation should preferably be monochromatic, and this is an obvious expectation because we say that the intensity of absorbance will depend on the wavelength and the molecule of interest. So as much as possible, a ray of light, which is of a single wavelength or a very narrow band, should be used for analysis. And sixth, the incident flux must not influence the atoms or molecules. In other words, the molecule should not become ionized. Okay, by the radiation. They will be excited from lower energy state to high energy state, but they will not be ionized. So in this case, we want the radiation to act as a non-invasive probe, okay, but not be an agent of change. So what are some of the limitations that are normally encountered in UV visible spectroscopy? Do you have any questions so far? Before we go to the limitations. Okay, so if there is no question, then we move on. There are some limitations or there are some challenges that are encountered when carrying out UV visible spectroscopy. And this can be classified into three. So there are those deviations that are real, they happen, they are expected because of the way the method operates. There are also deviations arising from chemical aspects of the molecule of the solutions. And then there are limitations arising from instrument components. Let's elaborate on these deviations. So in some cases, or in majority of the cases, very high concentrations cause the absorbance to become unproportional to the concentration. So in other words, we are saying that this method is applicable in dilute concentrations where the interactions between molecules is less likely. And these concentrations could be as a result of the molecule themselves or other materials incorporated in the solution to facilitate or to enable the analysis. So even buffers that are used to maintain a particular pH, which is a necessary condition in some cases, can alter absorbance. And in other cases, some molecules, even in low concentrations, show deviations. And we have listed an example there, which is methylene blue, and does not seem to obey the Beer-Roberts law, even at this very low concentration of 10 micromolar. The next set of limitation are the chemical deviations, and these are deviations that result from chemical phenomena, such as ionization, which is association and dissociation of molecules. So if, for example, you have weak acids and you measure at different pH values, then the proportion of dissociated and undissociated molecule will be different, and those two species behave differently in light, okay? So you'll find that those two species have different absorptivities, and that will affect the measurements. So you've given an example there of phenol red. So this is phenol red in basic and acidic medium. So in acidic medium, the colors are actually different, okay? And in basic medium, so if you were to measure the absorbance, you'd see a variance depending on the pH of the solution, okay? And you can see the intensities changing accordingly as the species or the relative proportions of the ionized and neutral molecule change. Then we have the instrumental deviations, and the instrumental we have various aspects. The first aspect is polychromatic radiation, and this is the use of or measuring the absorbance with a wide band of radiation, okay, or many wavelengths of radiation being used to assess absorbance. And to view this in a graphical way, if you were to plot the absorbance of a substance, we say that at the peak, as you measure absorbance, you find a peak, and the wavelength where the compound absorbs maximally is known as the lambda max. So if you use a band of radiation, let's say 5 nanometer width, so you are measuring using maybe 245 to 250 nanometers as your bandwidth. If you set the instrument at the particular wavelength, and then by error, you set at a slightly different wavelength. If you are outside the lambda max region, you'll find difference in absorbance from the lowest to the highest will be very high. So in other words, we are saying that the narrower the band, the more likely that you will get the relationship holding. Also, the choice of wavelength is very important. If you are to measure the absorbance outside the lambda max region, then the variation in absorbance between the highest and the lowest will be significant, and that will affect the measurement that you can make. So if we were to repeat that in a graph, see that when you use the lambda max, when you measure at lambda max, the linear relationship extends over a wider concentration range compared to when you measure outside the lambda max region. So that is the effect of polychromatic, right? Either the choice of a wide band for measurement or measuring away from the lambda max region of the compound. The other component of instrumental deviation is due to the presence of stray radiation. So when the light source, the radiation source in the equipment produces light, some of that light will be scattered by surfaces, mirrors, etc. And some of that light may eventually find their way to the detector. So the detector is not able to tell the difference radiation that has direct the radiation that is usually prevented by ensuring that the quality of the equipment You can hear me? Hello?
Yeah, you had been got lost. The screen is also lost now.
Okay, is it back?
No, the screen is not back.
It's okay now?
Yeah, it's back.
Okay. So I think we had come this far. So we are saying that in a dual beam, you are using a blank cuvette or a cuvette having the blank solution and the cuvette having the sample. If they do not have the same optical properties, then you'll find that the measurements may be erroneous. And if you were to plot um, the absorbance versus concentration, then you would get an intercept indicating that the two cuvettes have different optical characteristics. So how do we relate concentration to the amount or the amount of the substance to the absorbance? So we have mentioned that you can use molar absorptivity or specific absorptivity, and this is just an elaboration of that fact. So we are saying that if we know the absorptivity of the substance, or it can be calculated by measuring the absorbance if we know the concentration and the path length. Okay, so in this case, we are having a different molecule showing that if we had the same different absorbance, you need different concentrations to achieve the same the same absorbance. By applying the specific absorptivity, we simply replace the molar absorptivity in that equation, and we are saying that in the pharmaceutical field, we mainly use A1% 1 centimeter as the specific absorptivity, and this enables us to directly calculate the concentration in percentage terms in pharmacy. Okay. So this value can be determined or it can be picked up from the respective methodologies that are used. For example, if you are using for UV visible spectroscopy, which is a pharmacopoeia method, the pharmacopoeia method will give the A1% 1 centimeter of the particular compound of interest within when the specific conditions are implemented, and more so related to pH of the substance. Okay. Here we have an example of a common molecule, which is aspirin, and a common impurity found in aspirin. So we have aspirin and salicylic acid, and we can see how they absorb, the two absorb radiation at different wavelengths. Okay, and we can see that aspirin has low absorptivity compared to salicylic acid. And indeed, the lambda max are different because they are different molecules. But in terms of absorptivity, you can see they are quite different. So for quantitative application, if we were to plot absorbance against concentration, we'd have a portion which is linear, especially at lower concentrations. And then as concentration increases, the absorbance deviates from linearity. For example, for aspirin, the linear proportion is between 1 to 150 microgram per ml, and salicylic acid 2 to 80 microgram per ml. So that tells you that the absorbance will be linear for aspirin over a wider range of concentration compared to that of salicylic acid. And for measurement, for quantitative determinations, we always use the linear portion of the absorbance curve. So there are specific methods which are applied to determine the actual concentrations, and we can list them as single or double point standardization, calibration curve, standard deviation method. We can also determine concentrations when we have more than one absorbing compound. For example, if you are measuring absorbance of aspirin in presence of salicylic acid, you can actually determine the two. Then we have photometric titrations. This one you have mentioned earlier. And then we have what is known as indirect UV visible spectrophotometry. So let's briefly look at each of them. Single or double point standardization. So if we were to simply go back on this curve, we are saying that if your concentration, your sample is absorbing at a particular, has a particular absorbance, you can prepare two solutions of known concentration and measure absorbance, usually either slightly below and slightly above the concentration of the substance, and then you can estimate or calculate the concentration of the unknown by using an equation such as this. So this relates the concentration of the sample to that of the standard. So this is the for a single standard using just two concentrations, one of the standard and one of the unknown. That formula can be used for that calculation. We would go into the details of how you come to that, but it's something you can work out using the simple equation that we said relates concentration to absorbance. For direct calibration method, you simply prepare a series of concentrations, okay, measure absorbance, and then prepare the sample in the same way. By measuring the absorbance, okay, of the sample, and then drawing a line. You can, for example, draw do the graphical method like we have here. We have a graphical representation of the absorbance of the standards. And then you measure absorbance. You can now use that absorbance of the sample to work out the concentration of the unknown. Alternatively, you can simply use the equation of the line, okay, by plugging in the absorbance of the solution and directly calculating the concentration of the unknown. That is direct calibration method. A series of concentration of known concentrations of the solution are made, absorbance measured, and then from that you are able to extrapolate the absorbance or the concentration of an unknown by measuring the absorbance. This is a different method that is applied known as the standard addition method. And this method is generally used where it is not possible to account for background absorption. So if you have maybe a very complex medium, then a standard addition method is more applicable. And this works by adding a constant amount of the unknown to the standard solutions. So it's just like in the calibration method, but now instead of measuring the concentration, the absorbance of the pure standards, then you add the same quantity of the sample to the standard solutions. So that shifts the curve upwards, giving you an intercept. Okay. So in this case, known amount, a standard, that's a same amount of the sample is added to each of the standard solutions and the absorbance measured. So the intercept then gives you the absorbance due to the sample. Okay, so we are saying that that particular method is applicable to measurement where the background interference cannot be reliably accounted for. So you can use the same, if you have the equation, you can work out, but if you want to do graphical, you just extrapolate to the concentration axis and reading of the value of the concentration is going to be negative, but you take the absolute value as the concentration of the sample. All right. So if there are questions, just stop me and ask for clarification. The other method is used to analyze mixtures. Okay. And by this method is applicable because the total absorbance is due to the absorbance of the individual substances. So if we have many compounds absorbing, and we know that compounds absorb at all wavelengths, the difference is that they absorb maximally at different concentrations, at different wavelengths. So at any particular wavelength, the total absorbance is the contribution of each molecule present. So by applying the equation to the individual compound and getting the total, we can reliably determine the concentration of each by measuring absorbance at different wavelengths. So like, for example, if we had a mixture of two substances in solution, we just need to measure the absorbance of the solution at two different wavelengths. And by formulating two equations, okay? So if we take absorbance at one wavelength, okay, this is the lambda, one of maybe the lambda max of one of the molecules, and measure the absorbance, the total absorbance is given by that equation. Then we measure absorbance at the second wavelength, which could be the lambda max of the second molecule. We have another equation. So by solving these simultaneous equations, because we'll get the absorbance and at one wavelength and the absorbance at this wavelength, we know the particular concentration, we know the path length, and we know the absorptivity. Then we are able to calculate the concentration of the individual molecules. Then, in addition to that, we said that UV visible spectroscopy can be used to detect the endpoint during titration. Okay, that's what we call photometric titration. And we said the advantage of using spectroscopy as an endpoint detection method is the fact that you can use this method to titrate substances that are colored, which you would normally not be able to achieve with visual indicators of endpoint during titration. So depending on the spectroscopic behavior of the titrant, the product, and the titrant, we can get different types of curves. So in the first case, we can see that the absorbance increases and then flattens off. So what essentially this is telling us is that at the beginning, there is minimal absorbance. That means the analyte is not absorbing. But as the product between the titrant and the analyte is formed, absorbance increases. So in this case, only the product is absorbing. And then after a maximum, that means the reaction has ended, then there is no further increase in absorbance. In this particular case, even with addition of the titrant, absorbance does not change and then increases at the end point. So that means the product is not absorbing, the analyte is not absorbing, but the titrant is absorbing. And when it becomes in excess, then that's when we see the increase in absorbance. In the third case, absorbance is decreasing and then to a minimum value. So this means that the analyte is absorbing, but the product is not absorbing. In the fourth case, you can have the analyte absorbing, and as it reacts, the product is not absorbing, so the absorbance decreases to a minimum value and then increases because the titrant is also absorbing. So when it is in excess, then its absorbance will reflect. So the endpoint, okay, you can see this is a plot of absorbance versus volume of the titrant. So the endpoint is where you have the change in absorbance. So you'd to get the endpoint, you'd have to determine the value of the titrant or the volume of the titrant that corresponds to that change. So this method has various advantages that you enumerated earlier. So we are saying that photometric are usually more accurate compared to visual when there is subjectivity, especially when you are using the visual indicators, which is essentially determined by the ability to detect that change. It will vary from one individual to the next. In addition, photometric titrations are faster because you just need to measure absorbance by adding constant amounts. For example, you can add 2 volumes of the titrant, which will give you this line, and maybe 2 volumes that will give you this part of the line. And just by drawing those two, extending those 4 points, you are able to determine the endpoint rather than monitoring the additions as compared to when you are doing it using visual indicators. Okay. Third advantage is that even titrations which are slow at the endpoint can still be performed. Remember, we said that it is more difficult to carry out visual titrations where the reaction at the endpoint is slow. So, for example, if you are trying to determine the amount of a weak acid or a weak base, near the endpoint, you'll have the buffering affecting the transition that is happening. So it will be more difficult to determine the endpoint under those circumstances. But photometric titrations deals with that problem because you can put the excess and you are still able to get the two lines that will give you the endpoint. And finally, mixtures can easily be titrated with using photometric titrations by measuring the absorbance at the wavelength of the two analytes. Okay, so this is just a depiction of what you'd get if you are to use titration, photometric titration for two examples or for a mixture of two ions, bismuth and copper. Then we have what is known as indirect UV visible. So those that we have enumerated are direct applications. In some cases, UV visible spectroscopy may not be used directly, and we are giving certain examples with reasons. For example, in the first case, compounds that cannot absorb. Okay, so there some don't have strong chromophores. So this type of compounds can be derivatized, okay, reacted with other compounds to form complexes or to form compounds which can absorb strongly. And we have given an example of sugars which can be reacted with anthron in presence of sulfuric acid. They produce a compound which absorbs strongly at 625 nanometers, which then enables the application of UV visible spectroscopy. The second case is where there is irrelevant absorption. So, for example, in the assay of methyl testosterone, a reagent is normally added. And this reagent is usually of the hydrazide type. So there are many. So just select one. And then this facilitates the absorbance to be measured at 240 nanometers. Okay, so irrelevant absorption is due mainly to impurities, and derivatizing enables specific, okay, or increases the specificity of the method by eliminating absorbance due to other substances normally encountered in certain preparations. The third is to improve selectivity. Okay, so direct photometric titration of adrenaline as an example. There is a combination of adrenaline and lidocaine, and you want to determine the amount of adrenaline in that preparation, then procaine interferes with that. Not procaine, but chloropresol which is a preservative normally added in the multi-dose preparations, interferes with the measurement. So adrenaline can be reacted with iron 2, forming a purple derivative, and this then can be measured spectrophotometrically without the interference of chlorocreso. And then the fourth reason why indirect UV could be used is depending on the facilities available or the cost. So it is found that the instruments that operate within the visible range of the spectrum are usually cheaper. Okay? So you may find that some labs may not have the more expensive equipment, and they could go the indirect route to be able to analyze some compounds. So cost and availability of equipment could trigger the application of indirect UV visible spectroscopy. Finally, this is not a quantitative application, but it's just a manipulation of the data collected to be able to, for example, determine the purity of a material or the lambda max. And it is achieved by plotting the various derivatives, okay? Measuring, plotting the changes of absorbance relative to wavelength. Okay, so you can have the first derivative, second derivative, etc. And depending on the derivative, then you get different curves. For example, if you were to plot the first derivative of a peak, you'd see that the absorbance is increasing and then decreasing. So where that line intercepts the zero change, that gives you the lambda max. So this method is very useful for determining the lambda max. And if there was an interfering substance, then it will be clear when you plot absorbance against the first derivative of wavelength. So this derivative spectra can be used for better qualitative analysis and identification of the number of absorbing species. So we have said that if they are different, then you'll be able to determine how many they are and the lambda max. Then they are useful for determination of lambda max. We have seen that where the two, where there is the crossing of the zero line, then that gives you the lambda max. It's more obvious than when you're trying to work out that value using a peak. Then it's also useful when obtaining spectra in solutions with high scattering, okay? And it's easier to get a resolution where you have more than a single component in solution. So we have an example here where we have a mixture of two with lambda max, which are very close, okay? So if you were to plot the total absorbance, you would get two peaks like that. But then you can see it's a summation of the actual absorbances. If you were to plot the first derivative, then you are able to see that it's actually a mixture of two components, and the various lambda max are visible from that. So you very easily see that this gives you the lambda max of the first compound, and this is the lambda max of the second compound. So now this gives us a practice of what actually happens. So you have a sample of 20 tablets. So this is just an extract of a pharmacopoeia method. So a sample of 20 paracetamol tablets ground finely into powder, and the powder is equivalent to 20% of the average weight of the tablet, containing 100 milligram of active ingredient. So in addition, a series of paracetamol standard solutions was similarly prepared, and a graph of absorbance versus concentration was made as in the graph below. So which particular method is this among those ones that we said could be used to analyze substances? Among the methods that we have outlined, which method is this? Okay, that's direct calibration method. Okay, I said we speak up because I'm not able to monitor the chart as I'm sharing the screen. Okay, so this direct calibration method, the reason is we have a straight line which is passing through the origin. So that means that the standard solution is absorbing directly and proportionately. Okay. And maybe I could just mention something about these values. This R squared normally gives you the relationship between the variable that is being measured and the variable that is independent. Okay, so when it is very close to 1, it tells you that that relationship is strong, and you can say that the change observed is due to the change in the independent parameter. Okay, so that R squared value is very important, and for analytical methods, it should always be close to 1, usually above 0.99 figure. Okay. So here is the question: if the absorbance of the sample was 0.44, which concentration to that is closest to that of the paracetamol? So you have various values given there, but what you need to do is, given 0.44, you'd come and plot estimate 0.44, extend a horizontal line up to the point you bisect the line, the curve, and drop down to get the concentration from the concentration axis. Alternatively, you can plug 0.44 in this equation and calculate the exact amount. Okay. So what was the approximate content for the active ingredient in one tablet? So now you need to go back to the statement. So once you determine how much is present in that sample that was measured, then you need to determine the relationship between that amount and whatever was in the original tablet. So remember, whatever you read here is just 20% of the tablet. So what is 100% of the tablet? You look at that relationship and relate, because you normally be dealing with a tablet and not a portion of it. Okay, so that second question is asking you to relate the measured concentration to the content of the drug, of the formulation in question. Then, if you look at the pharmacopoeia normally gives a range. It will say the content should not be less than 90% or 95%, and not more than 105% or 110%, depending on the compound. Sometimes the range is even narrower, especially for very potent compounds. So whatever the pharmacopoeia says, then you need to determine, is that amount within the acceptable range given by the pharmacopoeia or the analytical method. So it's always very important to remember that you are relating your intention as to determine whether the tablet actually contains the amount within the accepted range. There will be tricks here and there, but that is the basis that you are able to work backwards to determine the actual amount, the actual content of the formulation, working from the concentration of the sample. And here is another example, 20 tablets of methyl dopa, accurately weighed, powdered, a mass containing an equivalent of 0.08 grams of anhydrous methyl dopa, weighed and quantitatively transferred to 100 ml volumetric flask, all that, okay? And then there could be specific questions asking whether it's a method, which type of method, is it standard addition, is it calibration method, or whatever, okay? So I'll share these slides so that you can work out these examples and to get a better understanding of all that. Any questions? Okay. So if there are no questions, then we'll call it a day for that. So if in case you have any issues, you can always contact me through my email, and then we'll be able to clarify any matters. So that brings us to the end of UV visible spectroscopy. And we'll look at other methods in due course. Stanley, we don't have another class with you. The timetable was changed. So we just have spectroscopy with you this semester. So otherwise, let's call it a day. We'll meet up next week. Hopefully, physical class, so that we are able to interact and understand each other better. Have a good day.